Geochemists have long measured ordinary chondrites to be incredibly hard. Laboratory testing shows these stones boast a tensile strength between 20 to 40 megapascals. That puts them on par with the strongest terrestrial rocks. Based on this metric, we naturally assume their parent asteroids are built like dense cosmic boulders. Yet, when we track these meteoroids entering Earth's atmosphere, almost all of them completely shatter at extremely high altitudes, long before they should fail. We are looking at a severe case of geochemical survivor bias. The fragments carefully studied in laboratories do not represent the bulk structure of the original asteroid. They are merely the densest, most flawless nodes that managed to survive the descent. To accurately measure the structural integrity of inner solar system material, we cannot look at the stones that land in the desert. We have to analyze the vast mass that is totally destroyed in the sky. That is the role of the European Fireball Network. They capture radiometric data from high-altitude superbolids using autonomous observatories spread across the continent. These instruments track a meteoroid's luminosity up to 5,000 times per second, generating light curves with extreme temporal resolution. Researchers apply a mathematical method called semi-empirical fragmentation modeling to these curves. It maps the recorded flashes of light directly back to physical mass loss. Simultaneously, photographic data records the meteoroid's exact trajectory, computing its precise deceleration as it punches into the air. By combining the deceleration trajectory with microsecond-level light capture, planetary scientists use the Earth's atmosphere as a giant hydraulic press to test the yield strength of meteoroids in real time. This plot is the radiometric light curve for Fireball 2015 August 26th, mapping absolute magnitude against relative time. The smooth, arc-like black dotted line represents theoretical steady-state ablation. This is how a solid, non-fragmenting body behaves as it burns. The jagged blue line is the actual radiometer data. It violently deviates from the theoretical baseline. To make sense of the data, researchers build a modeled fit, shown here as the solid red line, which closely tracks the raw blue readings. Those sudden spikes and prolonged humps are not random optical flares. They are mathematically quantifiable moments where chunks of mass detach from the main body. A light curve is a high-resolution millisecond by millisecond timeline of mechanical structural failure. The force tearing the meteoroid apart is dictated by the equation for dynamic pressure, P equals rho times v squared. As the body loses altitude, atmospheric density, rho, rises exponentially. This drives a massive surge in crushing force applied to the leading face. We can track the results of this pressure on the plot. Right around the 3.2 to 3.4 second mark, we see a cluster of sharp, rapid spikes. These short flares, modeled by the orange dashed lines underneath, mark the exact moment dynamic pressure breaches a yield threshold, triggering the instant release of millimeter-sized dust. Compare that to the green and purple dashed arches between 1.0 and 3.0 seconds. Those prolonged humps represent larger eroding fragments, slowly ablating alongside the main body. Researchers use the deceleration of the surviving leading fragment to calculate the exact dynamic pressure at the millisecond each of these fractures occurs. Mapping these luminous dust releases against sudden deceleration reveals the internal yield strength of the meteoroid at the exact moment it breaks. When we expand this analysis from one fireball to dozens of recorded falls, a clear structural pattern emerges. This chart tracks the surviving mass fraction of the leading fragment against increasing dynamic pressure on a logarithmic scale. Notice the first massive drop. At exceptionally low pressures, between 0.04 and 0.12 megapascals, the meteoroids experience phase 1 failure. In over 60% of cases, this initial failure destroys half the meteoroid's original mass immediately upon hitting the upper atmosphere. Surviving fragments experience a secondary period of stability, then shear apart in phase 2, between 0.5 and 5 megapascals. Laboratory tests on recovered stones show a tensile strength of 20 to 40 megapascals. Yet in the atmosphere, maximum failure occurs at just 5. These objects do not ablate smoothly or fail randomly. Their internal architecture forces them to shatter in two distinct, strictly quantized phases. Phase 1 failure reveals exactly how these bodies are built. The initial mass loss at low pressure is the stripping away of a weakly cemented, dusty matrix holding the larger structure together. This confirms that small asteroids in the 10-meter class are essentially rubble piles. They are reaccumulated debris from ancient cosmic collisions, not solid rock. Phase 2 failure, the secondary break at 0.5 to 5 megapascals, represents the structural shearing of the stronger constituent rock chunks along pre-existing internal microcracks. The presence of these internal fractures guarantees that even the solid blocks fail well below the theoretical tensile strength we measure in perfect laboratory samples. Semi-empirical modeling proves a macroporous architecture for inner solar system impactors. The parent bodies are far weaker than the individual stones they drop. This bimodal strength model dictates how we must approach planetary defense and kinetic impactor deflection strategies. Attempting to deflect a weakly cemented rubble pile requires highly specific kinetics to avoid simply shattering the body into a localized shotgun blast of debris. This fragile reality stands in stark contrast to the pristine, dense geochemical samples stored in our laboratories. We are looking at the ultimate survivor bias. The meteorites we study are merely the flawless anomalies that manage to survive the extreme gauntlet of atmospheric lithotripsy. Planetary science cannot rely solely on the stones that reach the ground. It requires reading the high-altitude light of what is destroyed to understand the true nature of the cosmos.